Synthetic division. Synthetic division is a way to divide polynomials. It's very handy in factoring polynomials, among other things. Synthetic division is a shortcut for long division, and so because it's a shortcut, it's got some limitations. First off, we can only divide polynomials by the form x minus k. So our dividend, what we're dividing by, must be x minus k. It's got to be linear. If it's quadratic or cubic, then we can't use synthetic division. When we're performing the synthetic division, an important thing to remember is if we're missing terms, we have to put in a zero placeholder. So let's look at some examples. Here I want to divide x cubed plus 6x squared minus 7 by x plus 3. Well, you may first think that's not in the form x minus k, it's x plus k. But if you think about it, x plus 3 can be rewritten as x minus negative 3, in which case we do have x minus k, where my k is negative 3. And so we can perform synthetic division. Our k is going to be negative 3. That is what goes outside of our box. Remember, with normal division, what you're dividing into goes inside the box. What you're dividing by goes outside the box. So outside, my box is upside down, and we use the coefficients of our dividend. So I get a coefficient of 1 for x cubed, a coefficient of 6 for x squared. Notice I'm missing an x term, so I must put in a zero placeholder for the x term, and then I get negative 7 for the constant term. Now, to perform the synthetic division, we add going vertically in the columns, and when we get those results, we multiply them by our k. So when I add in this column 1, there's nothing to add it to, so that 1 comes straight down. Now I take that 1 and I multiply by the negative 3. That gives me a negative 3. That goes in the second column, second row, so that now I can add the 6 and the negative 3 to get 3. Again, I take that result and I multiply by the k, so 3 times negative 3 gives me negative 9. Now vertically, I'm going to add 0 and negative 9 gives me negative 9. Again, I'm going to multiply by the k, so negative 9 times negative 3 gives me a positive 27. A negative 7 plus 27 gives me a positive 20. Now we just need to interpret that result. This last number here, this is my remainder. And this are the coefficients of a polynomial of 1 degree less than what I started with, than the dividend. So in this case, I had an x cubed, so my result is going to be an x squared. This was third degree, this will be second degree. So it'll be a quadratic. So these will be the coefficients, so x squared plus 3x minus 9 is my result, along with the remainder 20. Now what do we do with that remainder? Well, think about when you're dividing numbers. Let's say we had 26 and we were dividing that by 3. Well, it goes in there 8 times and we get a remainder of 2. Now yes, in elementary school we could put the little r in the 2. This isn't elementary school anymore. When you advanced in your mathematics, you learned that we either need to convert this to a decimal or a fraction. With a polynomial, a decimal is not going to make much sense, so we want to make it a fraction. Remember, to make it a fraction, we took the remainder, that became our numerator, and the divisor, what we divided by, became our denominator. And so we ended up with 8 2/3. It's probably also helpful to remember that that's the same as 8 plus 2/3. So 26 divided by 3 gave me 8 plus 2/3. So over here, x cubed plus 6x squared minus 7 divided by x plus 3 gives me x squared plus 3x minus 9 plus the remainder 20 over the dividend x plus 3. And so we get our result from dividing those polynomials. An interesting thing to note is that we could rewrite this. If we think about this division problem, rewriting it as a multiplication problem, we can see that that 26 would be equal to what I'm dividing by, the 3 times the 8 plus the remainder of 2. And you can see that 24 plus 2 does give us the 26. Rewriting it like that is using what is known as the division algorithm. We can do the same thing with polynomials. I can say that this quadratic, this cubic, x cubed plus 6x squared minus 7, my dividend, is equal to what I was dividing by, the x plus 3, times my quotient, the x squared plus 3x minus 9, plus my remainder of 20. And just like we did here, if you multiply and then add, you get 26. If you multiply these two together, add the 20, combine all your like terms, you'll end up with this. Let's look at a couple more examples. This one here. Notice I'm in the form of x minus k already, so my k is 2 this time. Again, that goes outside the box. Inside the box, I have 3, negative 12. Notice I'm missing an x squared term, so I need a 0, minus 1. I'm also missing a constant term. We need a 0 placeholder for that also. Performing the synthetic division, the 3 comes straight down. Multiply 3 times 2 to get 6. Negative 12 and 6 gives us a negative 6. Negative 6 times 2 gives us negative 12. Adding 0 and negative 12 gives us negative 12. Negative 12 times the 2 gives us a negative 24. Negative 1 and negative 24 gives us negative 25. Multiply the negative 25 by 2, we get negative 50. Adding that to the 0, negative 50. So again, there's my remainder. My result, my quotient, is 1 degree less. Since this was a 4th degree, this will be a 3rd degree. So we get 3x cubed minus 6x squared minus 12x minus 25 plus my remainder. Notice my remainder is a negative 50 over what I was dividing by was the x minus 2. If you had written this instead of plus and negative as just minus 50 over x minus 2, you get the same thing. And so there's our result for that division problem. One more example. This time I've got x plus 5, so I know that my k is going to be negative 5. My coefficients are 1, 5, negative 2, negative 10. So we're not missing any this time. We don't need any 0 placeholders. Bring down the 1, multiply by the negative 5. Add, we get 0. Multiply, we get 0. Add, we get negative 2. Multiply, we get positive 10. And add, we get 0. This time we've got a remainder of 0. My result is going to be, this was degree 3, my result will be degree 2. So I get an x squared plus 0x minus 2. So here's my result. But notice that since we have a 0 remainder, if we think about using the division algorithm like we did this one, then I could rewrite this. I'm just going to call this f of x to save a little time here. I can rewrite that. My f of x then would be equal to, so this polynomial would be equal to what I was dividing by, x plus 5, times the quotient, x squared minus 2, plus a 0 remainder. But notice adding 0 on the end doesn't change anything. It's not even necessary to be there. And so we have this, which looks like we've taken this polynomial and partially factored it. If we wanted to factor this, then we could completely factor this polynomial. So once we have the polynomial factored, or once we have a 0 remainder, then that tells us that this is a factor of f of x. Another special thing is if I were looking for x-intercepts, then I would replace f of x with 0. I would set each of my factors equal to 0. if you factored that one completely. And then solving for x, I would get x equal -5, which tells me this -5 is an x-intercept. It's also called a 0. It's also called a root. It's also called a solution. So when we get a 0 remainder, special things happen. Getting a 0 remainder tells us that our dividend, x plus 5, is a factor of the divisor. The divisor, x plus 5, is a factor of the dividend. The x cubed plus 5x squared minus 2x minus 10. It also tells us that this k, -5, is an x-intercept, a 0, a root, and a solution.